Okay, we will go through the exemplar problems in the class 12 physics chapter 8 electromagnetic waves. Okay, before going through this, we will see some basic things. So if you take a wave like this, the period of the wave is between these two cycles. This wave is repeating. Okay, here I have drawn for two cycles. So the time taken for this for one cycle is the period. Okay, this period is unit of this period is in seconds. Okay, so the time difference between these two repetition is also called wavelength, lambda, but the unit of lambda is in meters. Okay, the period is in time and lambda is in meter. So what unit they have given, whether it is in time or in meter, based on that you can find period or lambda. Okay, if they are given in seconds, so you can find only the period, not the wavelength. Okay, so the lambda is the wavelength. Okay, that is in meter. C is normal speed of light, and this is not v, it is mu, that is frequency. So it is looks like v. T time period. So 1 by t is the frequency. You can say f also. Not this is the speed of light, and this is the frequency of the wave, and you can also use f for the frequency, that is unit is hertz. Okay, t is in second, frequency is in hertz, and lambda is in meters. Okay, the other formula E equal to hv. H is Planck's constant, and E is the energy of the wave. Okay, this is the mu is the frequency. C, velocity of light equal to E by B, that is electric field by magnetic field. Okay, if they are given the electric field vector, magnetic field, then you can find the velocity of light. So momentum P equal to energy divided by the velocity of light. U is the energy of the EM wave. Okay, force is equal to momentum divided by time, delta P by delta T. Intensity equal to power divided by the area. Okay, these are the formulas given in this chapter. Intensity equal to power divided by the area. See, this is how a electromagnetic wave looks like. This is the electric field component, the red, and this is the magnetic field component. Electric field and magnetic field, they are perpendicular each other, and they are perpendicular to the direction of the propagation of the wave. If I say E is in X direction, B will be Y, and Z is the direction of propagation. Okay, so all the three are perpendicular in this. This is the direction of propagation of the wave. So all the three are perpendicular. One require 11 electron volt of energy to dissociate a carbon monoxide molecule into carbon and oxygen atoms. Okay, the minimum frequency of the applied electromagnetic wave to achieve this. Okay, see, this to dissociate the bond, we have to apply this many electron volt of energy. That energy comes from that electromagnetic wave. So they are asking the frequency of the applied electromagnetic radiation to achieve this. Okay, so we have to apply this energy equal to Planck's constant in the frequency. Okay, and then after finding the frequency, we have to map that frequency into the spectrum. Okay, this bond energy is from the electromagnetic radiation. Okay, E equal to hv. Planck's constant is this. So they are given the energy in electron volt. You have to convert the electron volt into joules using this conversion. So then finding the frequency, and this frequency is in the UV region. Okay. Okay, this falls here. Okay, this ultraviolet region. Okay, in this region. So that is why this chosen ultraviolet region. A linearly polarized electromagnetic wave was given as, okay, the E component of the electromagnetic wave is given, is incident normally and perfectly reflecting. Okay, normally perfectly reflecting in a infinite wall at Z equal to A, assuming that material of the wall is optically inactive, it is reflecting fully. The reflected wave will be given as, okay. So here they are saying horizontal perfectly reflecting wave. The EM reflected wave will have the phase change of 180 degrees. Okay. So reflected wave will this is the electromagnetic wave, and they want to make the phase changes. Then Z will be minus Z. The sign change will be there. So based on that, and this is the correct answer. Light with an energy, they are given the energy flux, they are given the flux falls on a non-reflecting surface at the normal incident. If the surface, they are given the area, and they are given the time. Okay, so they are asking the momentum. Given the energy flux, area, and the time, they are asking the momentum. Okay, 3. Okay, the energy flux into area into time. Okay, this much is the total energy. Total energy equal to energy flux into the area into the total time. Okay, the momentum is total energy divided by the velocity of light. So after that you will get this answer. This one. So here this example also similar. Okay, they are finding the energy use here from the energy flux into area into time, they are finding, then momentum. Okay, the similar thing you can use a similar formula. The electric field intensity produced by the radiations coming from this power 100-watt bulb is 3-meter distance is E. So the electric field intensity radiation from the power of the bulb is reduced both at the same distance. Okay, E is directly proportional to the power. Intensity is equal to power divided by the area. Okay, so the area is 3 square r square at 3-meter distance. 4 pi r square is 9. So this is 36 pi. 100 divided by 36 pi. For 50 watt it equal to 50 divided by 36 pi. So that is so it will be the new energy will be half of the old energy, that is 100 watts bulb energy. E means 50 watts will be half of that. Example 8.5. This is 8.4. Here also see power divided by area, the similar thing is given. Okay, you can go through this. Distance, power. If E and B represent the electric field and magnetic field of the electron. I already shown you how a EM electromagnetic wave looks like. It has a electric field component, magnetic field component. The direction of propagation is along, so the direction should be perpendicular to both of the thing. Okay. So it is important. It is E cross B, not the B cross E. Okay, not B cross E. It is important. Okay, so E cross B. This is electromagnetic wave. This direction is E cross B. Perpendicular. The ratio of the contributions made by the electric field and magnetic field common to the intensity of the EM wave. Here this important is intensity. So because there is a radiation pressure, in that electric field component is not contributing to the radiation pressure. So here they are asking the contribution to the intensity. So intensity is equal contribution, that is 1:1. Okay, 8.5. See, half of the intensity is provided by the electric field, half is provided by the intensity. For the intensity, half of the contribution by the electric field, half of the contribution by the magnetic field. So it is 1:1. The EM wave radiates outwards from a dipole antenna. There has the amplitude of the electric field. The electric field E, which transfers significant energy from the source, falls off us. So I equal to power by area. So I is directly proportional to the, say, 1 by A. That is, I is intensity is inversely proportional to the area. So that is inversely proportional to the distance R square. Okay, so the intensity of the electric field equal, this is given in this formula, intensity of the electric field formula. That means E square, electric field component, is inversely proportional to the distance. So E is inversely proportional to the distance. Here square, E square, R square. So E here R. Okay, so that means 1 by R. 1 by R. Electromagnetic wave travels in the vacuum in the Z direction. Okay, is given. Choose the correct options. Okay. IJK is a unit vectors. Okay, the associated magnetic field. Okay, there is a relation between electric field component, magnetic field component. So that is using the speed of light. Okay, E equal to CB. I already shown you. So based on that, B equal to E by C. Okay, so actually this is plus, because if you see here also minus, here also, what is the difference between these two? Here actually there is a plus. There is a typo here. So otherwise you see these two are same. So that is why this is a plus and this is minus. Okay, this option is correct. The given electromagnetic wave is plane polarized. Okay, it is in the same plane. Electromagnetic waves are plane polarized. Okay, it is polarized in the only one plane. Okay, the electromagnetic wave traveling in the Z axis is given. Okay, the direction of the propagation is Z axis. Choose the correct option. Okay, so now the associated magnetic field. Okay, this is based on that speed of light, electric field and magnetic field formula. Okay, this is direction of the propagation, electric field component, magnetic, all are perpendicular to each other. Okay, cross E. The electric field can be written in terms of the associated magnetic field. Okay, this is also correct. Because using that E equal to CB, and this is a unit vector. Okay, this is nothing to do with this relation. This is unit vector. This is dot product is 0 because dot product cos, because all are perpendicular to each other 90 degree, cos 90 is 0, that is why this dot product is 0. And dot product is this will be ke cos theta, theta 90 degree means it will 0. Then cross product okay, is not 0, that is why this is not correct. Okay, all these three options are correct. Okay, this can't be 0, this is 1 actually, so these three options are correct. A plane electromagnetic wave propagating along the x direction can have and be okay, and the main thing is all are perpendicular to each other. Okay, this is the direction of the propagation. X means these two should share the other two direction, that is y z. Okay, that is the thing. Okay, 11. A charged particle oscillates about its mean equilibrium position with the frequency the electromagnetic wave produce, that will have the same frequency. Okay, we have the wavelength, we have to use that formula. Okay, lambda lambda equal to c by v. Okay, the speed of light divided by the frequency. Fall in the region of this is the region and this spectrum. 15. Okay, radio waves, this is greater than the 0.1 meter. The source of the electromagnetic can be a charge. The accelerated charges actually radiate electromagnetic wave moving in a circular orbit, so it gets acceleration. Following the electric field, the charge get accelerated in the electric field. EM wave of intensity I falls on a surface kept in a vacuum and exerts the radiation pressure. Okay, you see this radiation pressure. See, electric field component is not responsible for the radiation pressure. Only the magnetic field component creates this radiation pressure. Okay, because electric field component is symmetrical in the positive and negative direction, so that will cancel out. Which of the following is true? Radiation pressure I see. Okay, 13. Momentum P equal to energy divided by the speed of light. Okay, energy divided by speed of light. Change in momentum when EM is observed, that is totally observed, so it is totally observed, the reflected momentum is 0, so it is totally observed. But if it is totally reflected, okay, this is the forward momentum and this is the reflected momentum, so 2I by C, when the total reflection, this is for the total absorption. Okay, radiation pulses in range. Okay, this is the range, this is for the total reflection, this is for the total absorption. Okay, 9. Okay, this is the energy. This is that for the complete complete absorption, this total energy will be absorbed. Okay, complete reflection will be 2 times that. Why is the orientation of the portable radio with respect to the broadcasting station important? Because of the alignment with the radio waves, because EM waves are polarized. As the electromagnetic waves are plane polarized, so the receiving antenna should be parallel to the electric magnetic field part of the wave. Why does the microwave oven heats up a food from the food item containing water molecules most efficiently? This oven, the frequency of the microwave is selected to match the resonant frequency of the water. Okay. Frequency of the microwave matches the resonant frequency of the water molecule. The charge on a parallel plate capacitor, the charge Q is given. The plates are very large and close together in the area A. The separation D. Declare the energy of the, find the displacement current through the capacitor. Okay, 16. For the AC source, the conduction current equal to the displacement current. So for the AC source, this charge is given IC equal to ID. This is for the AC current, AC source. So the rate of the differentiation of dq by dt, d of this. Okay, after that you will get this displacement current. A variable frequency AC source is connected to a capacitor. How will the displacement current change with the decrease in frequency? On decrease in the frequency, the reactance equal to 1 by the omega c. Okay, so the reactance will increase. Okay, will increase because this 1 by omega c. Decreasing the frequency means this will increase, which will lead to decrease in the conduction current. Okay, reactance increases means conduction current will decrease. In this case, both currents are same, so displacement current also will decrease. The magnetic field of a film covering on the form facing the floodlight is given. Okay, this is the magnetic field component is given. What is the average intensity of the beam? So that given is resembles to this equation. So from that is B. If you match this with this, so you will get this B naught equal to this one. Okay, then the intensity I average to this is the velocity of light, and this is the component. Okay, after that you will get this answer. The Poynting vector S is defined as the vector whose magnitude is equal to the wave intensity and whose direction is along the direction of the wave propagation. Okay, this is the definition. Okay, mathematically it is given E cross B 1 by mu naught E cross B. So show you the nature of the S on the graph. Okay, this is how that Poynting vector S varies with the Professor C.V. Raman surprised his students by suspending freely a tiny light ball in a transparent vacuum chamber. by reading the lower. Okay, which property of the EM wave, electromagnetic wave, or exhibiting this thing? Give one more example of this property. EM wave exert radiation pressure. Okay, electromagnetic waves exert radiation pressure. The another example is tolls of the comet. Okay, this I attached some reference videos. In that also, what is radiation pressure and example, the demo of the radiation pressure is given. Okay, you can go through that. Show that the magnetic field B at a point between the plates of the capacitor charging during the charging. Okay, during the charging, conduction current is 0 inside the capacitor, plates of the capacitor. Okay, so that is 21. This is the plates of the capacitor. Okay, this is the magnetic field between the capacitors. Okay, conduction current using this formula, flux equal to EA. Differentiation of the area. Differentiate E with respect to the time. The pi r square divided by the 2 pi r. Pi cancel out, r cancel out, top r these two, then you can put it here. Okay, r by 2 dE by dt. Electromagnetic waves with the wavelength. So these are the where they are used. Okay, which frequency is used in satellite communications? Satellite communication. Which frequency is used in the water purifiers? Okay, this is 22. This is microwave, this is ultraviolet, X-rays, infrared. Okay, so that is given in the book also. This frequency range is given in the book also. So that the average value of the radiant flux density as over a single period t is given. Okay, radiant this is the definition of the radiant flux density. Radiation emitted per unit solid angle and over a given wavelength interval by a point source. Okay, definition of the radiant flux density. Let us assume E is in X direction, B is in Y direction. So this vector and this is the cross product. Okay, we are going to use this formula, the electric field, magnetic field component, and the velocity of light relation. Okay, after this substitution and simplification, you will get this 1 by t. This simplification t by 2, t will cancel out and you will get this. You are given a capacitor, 2 megafarad plate capacitor. How would you establish instantaneous displacement current of 1 milliampere? ID displacement current of 1 milliampere you have to establish. Okay, this is the displacement current, capacitance, and rate of change of voltage. See, after thing you will get applying the very potential difference of this much, you will get the 1 milliampere current, displacement current of 1 milliampere. So that the radiation pressure exerted by the EM wave intensity I on a surface case is I by C. Okay, plus power equal to force by area. Force is equal to rate of change of momentum over the time. Okay, this is I equal to U by area into time. What happens to the intensity of light from a bulb if the distance from the bulb is doubled? Okay, as the laser beam travels around this, okay, it is not changing. Okay, 26. See here the intensity is the energy divided by the area. So for energy divided by the 4 pi r square. So if r is doubled, the distance is doubled, that is r becomes 2r. That means it's 2r square, that is 1 by 4, and here the same. So new intensity will be 1 by 4th of the this intensity. Okay, so if you double the distance, the intensity will be 1/4 of that intensity. Okay, generally these types of problem, the new intensity will be some multiples of the old this intensity. Okay, so you have to simplify this like that. So instead of r you put 2r, then you will get. So you have to, when the distance increases, intensity decreases at the rate of this 1 by r square. Okay, that is important. That is 1 by r square. Okay, the intensity is reduced to 1 by 4th. This is because the light beam spreads as it propagates in the spherical region over the area 4 pi r square, but the laser beam does not spread out. Okay, that is the main thing here. It does not spread out, and hence intensity remains constant. Okay, this laser does not spread out. That is important. Even the electric field exerts a force on the charge, the electric field of the EM does not contribute to the radiation. But that is the important. As I already told you, in the EM we have a electric and magnetic field component, but the electric field component does not contribute to the radiation pressure, because that cycle goes up and down equally. Okay, 27. The electric field of the EMA is oscillating field, and it is the electric force caused by it on a charged particle. So this electric force averaged over the integral number of cycle is 0, because it is up and down equally, that electric field component. So that is why it is 0. So it is not contributing to the radiation pressure. And infinitely long carrying the uniform. Okay, these all these things are given in the these answers are given. Okay, you can go through it. The 28, 29 all they given. Okay, for till the last thing they given. So you have to apply your mathematics integration differentiations thing also here. Okay.